We are live. You can go ahead.
Okay, so yeah, welcome everyone. Today is the third day, third tutorial, and today we'll be studying group testing. So I'll be covering the first part, and Suhail and Prerona will cover the second and third part. So my job, I'll be basically kind of setting up today's problem. All right, so yeah, the context of today's problem is something which has had the world in its grip since the past year and a half, which is obviously the SARS-CoV-2 virus. And yeah, as we have all seen that testing, just 1 minute. Okay. Yeah, so testing along with vaccination has played and is playing sort of a crucial role in keeping the pandemic under control and kind of maintaining some sort of normalcy in our lives. But when the cases are on the rise, typically we all have experienced it. Like it takes a lot of time and it's a lot of effort to kind of book a test and get results on time because the labs are swamped with samples, right? So that is a concern. And secondly, yeah, so in the news, you would have also seen this statistic called the positivity rate. All right. This is a very useful, this is an essential piece of information which we'll need in today's sort of tutorial because so let's just dive in. The question for today is that, can we test more efficiently? And efficiently is in double quotes. I'll come to it, what exactly we mean. So just mathematically speaking, the problem is very simple to understand. So let's say we want to test n people. All right, we want to test whether who all are COVID positive and who all are not COVID positive. So it is an n length binary vector. All right, and xi is 1 if person I is infected, it's 0 otherwise. And let S be the set of the infected people. So what is S? S is just what I mean, you can call the support of vector X, right? So X is, all I such that Xi is equal to 1. Now the assumption, like the main assumption which we'll work under is the fact that the size of S is less than equal to D, which means out of the n people, at most D can be positive. And we will not get into that. So the thing is, if we don't have this assumption, right, you can actually rigorously show that you can't give any guarantees. I mean, the thing is, if arbitrary, anyone can be infected, if D is in fact N, then you could sort of, you can probably intuitively guess that you cannot do any better than N test, in the sense that you cannot give a guarantee that I can do any better than N tests. So that is the thing. You can rigorously prove this, but we won't get into that in this tutorial. So we will work with the assumption that size of S is less than equal to D. So you sort of can, rationalize this assumption as, So you can sort of, think of it this way, that D by N is sort of the positivity rate that we are kind of seeing at the moment, right? And the minor assumptions we make are that pooling is possible and tests are accurate. The thing is, because pooling, in some class of problems, it might not be possible. It depends on the kind of infrastructure you have for testing. So that's fine. So mainly its size of S is less than equal to D. The test, what is the test? What is the pooled test? It is just the Boolean sum of inputs. So let us say, like if I group 1, 2, 3. So what output? So what is the output of the test? It's just X1 or X2 or X3. So any one of if any one of them is infected, I'll see that the test result is positive, else it's negative.
Eeshan, do you want to instead say Boolean OR of inputs?
Okay,
instead of some?
Yes, let's just do that.
I think some we were using as XOR in some instances, just to make sure.
Yeah. So for example, so it's basically, let's say if I feed X1, X2, X3, what I'll get is just, Xi is equal to 1, 2, 3, whatever. All right. And the goal is simple. We just want to recover X, or basically the infected set S, such that the number, what we want is that number of tests should be less than N. You can obviously do it with N. Can we do it with less than N is the question here. So this is, I think, I hope that this is very clear, because it's quite simple. And now, we know of a way to find, all of us will know of a way to find a particular element in an array. If you are looking in an array and we are kind of trying to find something, how do you do that? What is the method? Can anyone tell me? How do you find a particular element in an array?
It's a sorted array, right?
Yeah, I mean, okay. So, okay, just think about it. Okay, okay. I mean, I should have said, okay. So the thing is, let me just fill it up myself. Okay, just think about this thing. Like, how can you use binary search? Let's say if I tell you, okay, that you can do something with binary search. How can you use binary search to solve, let's say, to find a defective element, like in this particular setting, like we have.
There is a defective element here. There's a C missing in search.
Wow. Wow. Thanks. Okay. So yeah, let's can you think about it? Like just give it a shot. Like what is the first test you would sort of, like let's say, let us say there is only one defective element. Let us say there is only one positive person in this n length vector. How would you go about it? Any idea? Can someone tell me? Like, okay, so let's say, like,
By the way, is the task clear to people? Are there questions about the task?
hello? Yeah.
I mean, so
Let's,
I mean,
maybe you can.
Please feel free to unmute yourself and ask and so on. So right now, what we are basically saying is that, there is a small number of infected people in a fairly large population, and we are trying to find out who they are. Now, we can, of course, test everybody in the population, but that seems wasteful. So what we are trying to do is, can we do something else? So for example, if you test 100 people together, that is, you combine all their samples and just run a PCR test or something. If it turns out positive, one of them is positive, but you don't know who they are. So the question is, can you somehow use tests to narrow down who these positive people are?
Is it clear? Is it all right? Anyone? Maybe Tania? Is she there? I don't know. What has happened? I mean,
I think one of the general polling things, general checking.
So this clearly vague thing, that one. Okay. Perhaps we'll get probably clearly vague. Okay. So I think shall we? Yeah, I think I'll go over it again. I think 4-6, right? Yeah, in favor of vaguely clear. Okay, so it's quite simple. So the thing is, okay, let's just go back. I mean, okay, what is the simplest thing you could have done, right? I mean, let's say you just had to identify who the infected people are in this set of n people. What do you typically do without pooling? You just test them individually, right? And you'll figure out exactly with n test who exactly is infected. Now, what we are saying is, let's say we have some extra piece of information, and that piece of information is, is basically tied to what we call the positivity rate. So essentially, I tell you that only up to at max d people are infected in this set of n people. Can I do something better? And also, I'm allowed to pool tests. Meaning, instead of, let's say, so let's say, let's say x1 being tested individually, x2 being tested individually. Can I pool the swabs, the samples from x1 and x2? Test them together and see their output. All right. And I'm telling you that how that output is basically the OR of x1 and x2, meaning that if either of the two is infected, my output will be 1. If neither are infected, then only the output will be 0. All right. So the thing is, I tell you that this is how the pooling is happening. Now the question is, can I perform less than n tests to figure out who is infected and who is not infected? I want to recover. Hello. Yeah. I mean, is it clear? I mean, is this clear or not? I mean, can anyone answer? Just yes or no.
Yes, it's clear.
Yeah. Thanks. Okay. Okay, so I'll just, I mean, yeah. So let's say, I'll give you a hint. So the thing is, okay, I have this vector. No, not, yeah. So
someone has mentioned in the chat the randomized.
Yes. So no, we are not doing randomized tests. We are just like, it's all deterministic here. And I'm also assuming that my test results are also completely accurate. I mean, there is nothing randomized here. It's all deterministic. At least today's tutorial is completely deterministic. So this is the thing. All right. So now, yeah. So right. So the thing is, okay. Let's say I split up this n-length vector into two parts. All right, and I pool the second half. This, let's say I perform this test first. I pool all the participants. So my test one is basically I pool all the participants here. And let us say again, we are dealing with the simplest case, like that D is 1. There is at least, there is at most one person. I mean, at most one person is infected. Now what can I do? Like, okay, I'll observe something. After that, what can I do? Can anyone tell me like what the next test would be, logically speaking? You have seen, I think, just apply the same logic of binary search. What would you do next? I mean, let's say, let me tell you one more thing. Let us say the output of this test is 1. What does that mean? The output, so the XOR here, right? The XOR of all these Xi's happens to be 1. What does that? Oh, sorry, it's not sorry. Or of Xi's happens to be 1. What does that mean?
And the infected at least
positive here, we can again do binary, divide them and check them.
Yes, exactly. So the thing is, and then I'll again split it into half. I'll try to see in which half is the infected person actually in, and I'll keep doing that. All right. And this is how you would this is how you actually will end up, and you will end up finding this particular element in sort of, what's the order of, like, what's the time you will take? Like, typically what time do you take? I'll just fill it up, but right, correct. Now, this naive approach, this naive way of doing binary search, you can actually extend it to D elements also. Now I have to find, instead of one defective element, one infected person, I want to find, let's say now I have up to D infected people. So the most naive way to extend this approach would be what? I will do this for one person. I'll discard that. I'll set aside that person. I'll again perform binary search over the n-1 length vector and so on, right? So typically, what's the order? Like, what sort of time will it take? I mean, I think that you should be convinced that it will take, let's say, is this fine? Essentially, I'm repeating this binary search for, like up to D times, because I know for a fact that, there are only up to D infected people in this set of n people. Is this okay? At least the first, the binary search logic, like how you can use binary search to find out these positive cases, that much is clear, right? I mean, because some of you, that's fine, right? Hello?
Yeah, Rishona gives a thumbs up. So
okay, sure. Okay, yeah. So I'm just relying on Rishona's this thing. Okay. So, okay, but then there is the question of, there is something, this is what we call as an adaptive test. And why is that? So the thing is, as I told you, right, first test, I just kind of arbitrarily chose, okay, I'll just pick up the second half. I'll just pull all the samples in the second half and I'll see what result do I get. But the second test, the second pool test, what was it? It depended on the output of the first test. Had the first test come out to be negative, if the OR of the Xi's in the second half was negative, I would have then looked at the first half, right? Because I don't have any positive cases in the second half. So I would have looked at the first half, and it was not the case. If the OR was indeed positive, the OR was indeed 1, then I would have again, I just picked up some half in this second half, and I would have repeated this operation. Meaning so what I'm trying to say is just this thing, that so my ith pool test depends on the outcome of the previous tests. This is very clear, right?
Yes, sir.
Yeah. And this is not a good thing. Imagine the frustration of the lab technicians, right? They just have to sort of, for each test, they have to see, okay, what result have we got? Now, what next do we have to do? This is just infeasible, logistically infeasible. So that is sort of, that is the pitfall of using binary search to solve this particular problem. So we want something which is non-adaptive. And before I come to what exactly or how exactly a non-adaptive test looks, I'll just quickly, we have to cover something. So you just think about this simple problem, that what did I tell you, right? I mean, so just tell me. So yeah, let's just try to solve this thing. How many possible x vectors are there? I mean, for what I'm asking is this, how many x n length vectors are, how many n length binary vectors are there such that number of ones is less than equal to d? And I call this number capital N. There is a subscript n comma d, but let's just call it capital N. So let's just try to see what that number turns out to be. All right. Let's just try with the simplest case again. If d was 1, then what is capital N? I mean, how many possible vectors, n length binary vectors are there such that they have only one? Someone? Sorry, I didn't hear. Huh?
So I heard an n choose d, but it's very faint.
Yeah, I think Janaki, yeah. So n
Yeah.
choose d, so n choose, yeah, but I mean, so, okay, the assumption is it's less than equal to, it's not equal to.
Yeah, sum it over all these.
Yeah, exactly, you're right. So yeah, so that's exactly what it is. So yeah, I mean, I just have to dot, which is, as Janaki said, it's just, sorry, 0 to d. And just believe me, I mean, you can show that, this is in fact, there is some bound, you can show that it's upper bounded by this sort of quantity. So you can just say that it's about, order of, let's say, like n by d power d, something like this. All right. So yeah, this is sort of the number. This is the sort of the number of all possible configurations. And our goal is to kind of, recover the exact vector x from these many sort of possibilities. So yeah, this part is clear, right? I mean, yeah, this part, yeah. So let's just, if not, then just stop me. I'll just go back again. So now we come to non-adaptive test, right? So by non-adaptive, what do I mean, right? It's like, someone, I mean, if I am a lab technician, right? I want you to tell me precisely what the tests I should perform, So, and yeah, and I want to look at the outcome of those tests and just figure out, okay, these are the people who are infected. That is my job. I don't want to just do test 1, then see its outcome, then decide what test 2 I should perform, and so on. And as you can see, I mean, yeah, the correct way to kind of, like encapsulate this idea of non-adaptive testing is, by just having a matrix. And this matrix is basically an R cross N matrix. So R is the number of tests. Let us say R is the number of tests we will be doing. So that is, those are, so the number of, so each row here, right? So each row here is a test. All right, so I just mention here, each row is a test and each column is an individual or a person. So we have n columns for n people, and we have R rows for each test. And you see, like, okay, row 1 is basically, you can immediately sort of, like, I mean, understand. So that's like, yeah, so row 1 essentially I'm pooling sample 1, sample 3, sample n. Row 2 I'm pooling sample 2, sample n, and so on. So typically this matrix, I call this matrix capital M. So capital M, Mij is 1, Mij is 1 if j is included in test I. All right. And it's 0 otherwise. So let's just take an example. I think it's already clear to you, but let's just take an example. So let's say I take I is equal to 1 and j is equal to 3. So the entry here is 1, which just says that person 3 is included in test 1. All right. And for each test, I have an outcome y. All right. So I have y1 to yr, like, because there are r tests. And what is yi? Yi is just the OR of the ith row. So for example, I fix the ith row and I vary j from 1 to n. So I just see, okay, in that row, who all are pooled, I just, sort of OR them. And that is how I get the outcome of the ith test. All right.
You OR the x variables.
Yeah, I OR the x variables. Yeah, sorry.
So
Oh, sorry. Yeah. So sorry. Yeah. So okay. Wait. So, yeah. Sorry. So okay. How should I write this? It should be like.
You OR all the
yeah,
xj
so
such that Mij is 1.
Yeah, right. So right? Such that, yeah. I'll just, yeah, maybe, I think, yeah, I just maybe messed it up a little bit, but I think it should be clear in English at least. So I'll look, sorry, yeah, this sort of not exactly, yeah. So the thing is, let's take an example. Let's test 3. So it has like 1, 1, 1, and then so 0. Let's say, so then what does that mean? So I'm basically pooling person 1, person 2, person 3's samples. So which means the outcome Y3 should be, I mean, it should be like, let's say I'll just or it here itself. So X1 or X2 or X3 and so on, right? So is this clear? Yeah, I mean, sorry for this thing, but is it clear? Like what exactly why I looks like? Hello?
So basically, you're XORing all of the
Oring.
Not the XOR, but it's the
or. Okay.
Yeah,
Sorry,
yeah. Right, exactly. Yeah. So I had messed up. I just wrote the matrix side and like the entry in the matrix, but that is not the case, as Suhail and RP pointed out. Yeah, it's basically, yeah, I'll just see, okay, who all are pulled in that particular test, and I'll or the xi, x corresponding xi's basically. So if 1, 2, 3 are pulled, I'll XOR x1 or x2 or x3. So
I mean, it's basically what you would
yeah,
think should happen, right? I mean,
yes.
you are combining 1, 2, and 3. If any of them turn out to be positive, the test should be positive. If all of them are negative, then the test will be negative.
Right. So yeah, I hope I'm clear. I mean, yeah. So I hope, yeah. Yeah. So the thing is, yeah. So now let's just look at this thing. What are the total number of possible outcomes? We did look at the total number of possible configurations of X, like how many possibilities of X are there under the constraint that number of ones is at most D. Now let us look. I mean, it's just very clear that okay, what's the total number of possible outcomes of these R tests? Any answer? Like it just, yeah. So it's what is Y? Y is a R length 0, 1 vector. So how many possible outcomes do I have? It is 2 to the power R, right? Fine. Hello.
Yes.
Yeah. So now I want to, like, yeah. Now the thing is this number, right? The number of total possible outcomes has to be greater than equal to something. Can you sort of think about it? Like what has to, like it has to be greater than equal to what? Like what do I want, right? I want, like, I'll see one possible outcome, and I have to map it back. I have to kind of somehow figure out what X gave me this outcome. And just think about it. Like what should be greater than equal to? So let's just, yeah, I mean, it was there on the previous, the previous page. Maybe just kind of try. Can anyone reason out, like, or maybe just, yeah, and like the number of possible outcomes has to be greater than equal to what?
Yeah, so greater than equal to the number of possible.
A bit faint. Can you just speak a bit louder?
Yeah, so it should be greater than equal to the number of possible.
Exactly. I mean, at least this much, right? Yeah. And why? Yeah. So it has to be, so we just kind of evaluated something here, right? We kind of evaluated the total number of possible X's, all right, under the assumption. So it has to be greater than equal to, it has to be, I'll just skip the subscript here. So I'll just write it capital N. And why is it so? Because had it not been the case, right, then it should be, we just try to think of this way, right? I mean, then definitely two different X's, right, will be inevitably be mapped to a particular outcome, right? I mean, if the total number of outcomes is not greater than equal to the total number of input configurations, then two different input configurations will inevitably map to some outcome, and then I have no way to kind of figure out, right, that which X actually gave me this outcome. Like so is that fine? I won't be able to recover X. That's clear, right? Is it clear?
Yes, sir.
right? So now I just take the log on both sides, just ignore this theta notation. Essentially, I have something like, R should, the order of R, it should be something like, yeah. So I at least need these many order of tests, D log n by D or something of that sort. Because of the simple argument that, I mean, every different configuration should map to a unique outcome. If that is not the case, I cannot give any guarantees about recovery. So that is the bare minimum number of tests I need to have. Now, okay, but still the problem is not resolved. So wait, yeah, let's see. So yeah, I mean, I think I'll try to finish in like maybe, I mean, my part in maybe 5-7 minutes. Let's see. Okay. I see. So now the thing is, let us make one more assumption. No? Like the thing is, M is such that for each X, there is a unique outcome Y. Now, so the thing is, yeah, this is something which we'll call in this tutorial as the matrix guarantee. All right. So the thing is, what I'm telling you, let's say you have a matrix. So you're a matrix M for, a matrix M satisfies this assumption that you give me a particular, you give me an X, it will map it to some unique outcome. So each different X has a unique outcome Y. Now, can you come up with like, first of all, do you understand this assumption? Like, is this assumption clear? Is this fine, or should I repeat or anything? Can you just anyone answer? Like, so what I'm telling is basically, it's what I guess what would you call is like this injective function or something, right? So each X is being mapped to a unique Y. That is all the assumption one is telling me. And I say that, okay, I mean, let us assume that, okay, matrix M satisfies this. This sort of, this assumption. So like, is this clear? Is the matrix guarantee clear? I mean, is this assumption clear?
Yes.
Yes,
Clear, right? So now let's just try to come up with the simplest, like the simplest algorithm to recover X. And I'll just give you I think it should, maybe some of you only will answer it, but I'll just give you a hint. Let's say you have some function. I know this, let's say this is injective function F. All right, F is injective. And you can just, and it takes some input, all right. And I observe the output, let's say A or whatever, I observe some output. I want to find out what the input was, which gave me A. So what can I do? Like, I mean, the most basic thing, what can I do? Can you just maybe think about it? Like, say, maybe take 2 minutes, take a minute or two and just try to think about it. What can you do? Just like there is no constraint on time, complexity, anything. You just, I know that each element in the domain is mapped to a unique element in the range. So what, how do I recover the input by observing the output? What can I do?
brute force on the domain level.
Exactly. So that's the thing. You just try out. I mean, so algorithm one is just that. Just, for all, like I in 1 to capital N, just run the test basically, so just run the test. I mean, run these tests, this entire matrix, basically all these are tests, whichever output matches, right? So you'll, at some point you will see that, okay, no, for some output that, I mean, the corresponding input. I mean, I think I've just written it like not very cleanly, but you get the point, right? So I'll just basically, I think this is not a nice way of writing this, but yeah. So basically, okay, so you just run the test, all right, for each particular X, just run the test. At some point, you will see that I get the output which I'm observing. And then that is basically, that is the X, which, because each X is mapped to unique Y. So if you have stumbled upon the correct X, which gives you the observed Y, that is the X which you're looking for. Is this clear? Like, maybe you can just ask me, like, yeah. Could have explained it in a slightly better manner, but that's fine.
It's clear, sir.
It's clear, right? Right. But then, I mean, as you can just clearly see, it's taking, it's terribly inefficient, right? I mean, you're essentially taking, like, I mean, you're running through like capital N iterations, and the size of the matrix is just R cross N, right? So that's like definitely not the correct, like the best way. So now I have some sort of, I try this sort of simple algorithm, all right? So I essentially decide that, like let's say initialize my infected, like this S is the infected set, all right? Then I initialize S with like basically 1 to N. I said that everyone is, let everyone be infected, all right? And then I run the tests from 1 to R, and then I do this thing, if yi is 0, then from the set S, I will remove the support of the row I. For example, if I just go upstairs, let us say, let us say like test 3. So yeah. Oops. Yeah, let's say test 3 gave me, let's say I got that y3 was 0 here. I can surely say that, that 1, 2, and 3 are not infected, right? I mean, their OR is 0. So surely, I mean, the thing is x1 or x2 or x3 is 0. So definitely each of them is not infected. They are all zeros. They are not infected, right? So I can acquit them in some sense. I can just, like I can say, okay, they need not be in this infected set. So I subtract them from the infected set and just repeat it for all these N tests, for all these R tests. And at the end of it, I just output whatever is remaining in S. So I start with that S has everything, all are infected 1 to N. And if at any point of, for any test which has 0 output, I just, subtract, I mean, I'll subtract the support of that particular row, and I'll just do it for R and I'll just return S. So is this algorithm is clear? Like this very simple algorithm. Like we'll just see if it works or not. Is this clear? Like is the algorithm clear?
So in this case, the support was those 1, 2, and 3, right?
Yes.
So you remove them. That's it.
Yes, that's it.
Okay.
That's clear. Yeah. So that's exactly what is happening. And if yi is 1, then I don't do anything, because I'm not in the position to let anyone off the hook in some sense.
You can't decide which one is
Exactly.
infected. Okay.
So now this is the thing. So this is the algorithm. Now the question is whether it will fail or not. I mean, whether it will work or whether it will fail. And if it fails, when does it fail precisely? So just 2 more minutes. I think I've just sort of overshot my time, but it's maybe finish. Yeah. So the thing is, just think about this. I think I'll launch so the thing is, I mean, the answer is already there on this page itself. So how do I launch the poll? I mean, let me just check. The second. Okay. Yeah.
Sorry, which poll do you want me to launch, or are you launching it?
Hi, I'll launch it.
Okay, cool.
Okay, so the answer, I mean, I'll just, it's a big hint. So it's just there on the page itself. So yeah, just think about it. What kind of errors?
By the way, the question seems to have been somehow hidden.
Oh.
So what kind of errors will what?
Okay, so what kind of errors will algorithm 2 have? That's the question.
Okay.
Yeah, I just expanded the thing.
Okay.
Yeah. So it's fine. At least I have a thin majority, but it's like, yeah, okay, not quite. It seems okay, I think. Yeah, there is, so the correct, I mean, everyone is guilty unless proven innocent, right? So the thing is, I mean, as you can see, right? I mean, what is happening, right? I mean, at this point, I'll just probably hand it over to Suhail, but I'll just kind of, let's take a minute more. So it's like, just think about, will this algorithm really classify an infected person as not infected? I mean, what is happening if I'm only acting, I'm starting with the thing that everyone is infected, and I'm only taking an action if I observe that some y is 0. Only then am I doing something. So that is the thing. Maybe I'll end polling. I mean, there is so it's fine. So I'll just end with this toy example. Just think about it, like it's n is equal to 2 and d is equal to 1. All right. So there is 2 people and at most one of them is infected. And I'm working with this matrix. So the row is 1, 0 and 1, 1. Just see what is happening here. All right. So the thing is, if I, so what, first of all, what possible x's are there with this assumption that d is equal to 1? I just have 0, 0, 0, 1 and 1, 0. I don't have 1, 1 because d is 1, right? So both cannot be infected. Now, y for x, like when x is 0, 0, y has to be obviously 0, 0. And when x is 0, 1, which means the second person is infected. So then the output, right? So basically, like I'll just write it here. So wait. So x1 or x2, oh, sorry. x1 and x1 or x2. So the thing is here, like the output y will be just 0, 1. But what is happening here, right? Here my output will be 1, 1. So the matrix, so the thing is there is in fact a unique mapping, each different x is in fact being mapped to a unique element, is being mapped to a unique outcome. All right, there is no confusion here, but there is some sort of incorrectness and there is some error happening in this box, right? I mean, when string x is 1, 0, my outcome is 1, 1 actually. So something, I mean, yeah, so there is something going wrong. So at this point, so the thing is, it seems that, we need one more assumption about m. But the question is that, are we asking for too much? Are we asking for too many assumptions? And it turns out that not quite, like you can actually, with some neat mathematics, you can actually, make things work pretty cleanly. So yeah, at this point, I'll just let Suhail, take over, I think, yeah. So some little parts I missed, but it's okay. Okay, Suhail, over to you. I'll just stop sharing.
Okay.
Just 1 minute.
Let me share mine.
Where is this? Yeah.
All right. So can everyone see my screen?
Yes. Yeah.
So yeah, I'm Suhail. I will be continuing in the second part where we're going to analyze this algorithm 2, where everyone is guilty until proven innocent. And basically algorithm 2 behind it is it's using some very simple steps. It's finding out who all have participated in tests where the test turned out to be negative. So anybody who participated in a test that turned out to be negative is obviously going to be negative themselves. If they were positive, then the test would have been positive. So you eliminate all those people, and then whoever is left, you output them as positive, right? So this is, yeah. This is algorithm 2. And suppose that you have a set of infected people, as before, we're going to call that set S. Then the output of this algorithm 2, we're going to refer to that output as A of S. And what we want, ideally, is that A of S should be equal to S. The output of the algorithm should be same as the actual set of infected people. So ideally, A of S is equal to S. Now, A of S, let's see what A of S depends on. So A of S definitely, it depends on S, because based on the set of infected people, the output of the algorithm is going to change. If S was empty, if there were no infected people, then you would guess that A of S will also be empty. It need not be empty, but we would want it to be empty. And the reason it need not be empty is A of S also depends on which tests we have chosen. It depends on our matrix M. So if we've chosen a bad set of tests, then it's possible that A of S is not equal to S. For example, in the example that Eeshan just showed, A of S would not have actually been equal to S in the last case. So we need to choose a set of pool tests wisely so that for all S of size at most D, A of S is equal to S. Now I'll state this again. Right? Yeah. So we say that our set of pool tests has been wisely chosen if for all of our possible set of infected people. So this is like we're doing hypotheticals. We're saying, what if S was this particular set of size at most D? So this is the possible infections, possible infected configurations. And we want for every possible infected configuration, A of S should be equal to S. Okay. And this is when we say that the set of pool tests is good. Now let's analyze this one condition. What we do know, what we just saw, is that it doesn't matter how bad we choose our tests, this condition is always going to be satisfied. Right? So just imagine it, suppose P was in S, that means P is to be thought of as an infected person. Then every test that P appears in, that test will come out to be positive. So P is never actually going to be removed from the answers of AS. So if P is in S, then P is in AS. So we don't need to use any cleverness to ensure that S is a superset, S is a subset of AS. Where our cleverness comes in, where we need to actually use some logic, is for the other direction. We want that A of S should not be any larger than S. So let's just state this again in mathematics. What we want is that for any possible infection configuration, and for any person who is outside of the infected list of people, that person should also be outside the output of the algorithm. So these are all the infected people S. This is non-infected. And here it's saying that it should be marked as non-infected. So what we've written here, this statement is exactly the same as being good for algorithm 2. So this is actually just the same as this. We've just rephrased it in a more mathematical way. And the reason why we want to phrase it in a more mathematical way is because the place where algorithm 2 is most useful is that it allows us to switch from English and from just, simple thoughts like our test should be good. It allows us to go from there to a precise mathematical statement that is easier to deal with. So let's see this. So we know what being good for algorithm 2 means. From this, we can figure out what does being bad mean. So your tests are not good tests if and only if there is some set S of size at most D, and there is a person who is not infected. If the set S was the set of infected people, there's a person who is not infected, but that person has been output as infected. Right, so the English here is, we're doing a hypothetical here. We're saying there is some set of size at most D. If those people were infected and there was another person who was not infected, such that that person was being marked as infected, that is the only case when we will conclude that our tests are bad. Okay, so I just want to know if, if people have followed here. We launch this? No.
So Suhail, do you want me to launch a poll?
Yeah, I'm launching it.
Oh, okay, you're launching. Okay.
So the question here is, how clear is this condition? When do we say that our tests are bad as far as algorithm 2 is concerned? Okay. So it looks like it's clear for quite a few people. It's also vaguely clear for quite a few people. If it is vaguely clear, if you have any question that can be clarifying to you, please unmute yourselves and ask it. That would be the ideal action for you to do. Hopefully it should get clear as we move along, because we're going to look at actual examples. Okay. So now we're going to look at this. When is a test bad? P is not in S, but P is still in the output of the algorithm. And right now I want all of you to actually figure out, how is it possible for this to happen? So remember, P over here is a person. Okay, so we're actually dealing with human people here. So let's try to empathize with them. So imagine you are this person P. You know that you're not infected. Somehow you're just sure that you're not infected. But you've gone to the hospital and you've given your sample anyway, just to get tested. And the hospital takes your sample and it takes multiple other people's samples as well. And then they run some tests. And then after running those tests, they come back to you and they say, algorithm 2 says that you are infected. Now I want you to figure out, how is this possible? You know that you're not infected, but algorithm 2 actually says that you're infected. So I'll pause here and wait for some answer.
Does this mean that the test was never carried out on this person's sample?
So that is one possible case. So if that's right, so if no test was done, no test with P, then the algorithm has never actually categorized this person as negative. So then P will belong to AS. But there are other ways also for this to happen.
If like we are taking an order, right? So it's possible that because of that this person got.
That's right. So can we elaborate a little more? So we're taking an OR, and what should happen for that OR to actually become 1, even though we are 0?
Others like the people who have we have taken OR with, they are infected.
Yes. So as far as one test is concerned, this is correct. So if there is a test that includes P and somebody from S, then that test will turn out to be positive. But just because that test is positive, does it mean that P is going to be in A of S?
In every case where P is included there.
Exactly. So that's exactly the condition. So if every test, including P, also has somebody from S, then P is in A of S. And in fact, this is the only way that it can fail. So if this happens, so this is obviously bad for us. And what is the good thing? It just has to be that
There's just at least one
exactly
test.
just one test where P is included, but nobody from S. Great. So this is an exact characterization of when your tests are bad for algorithm 2. And I'm going to call this as P is in the shadow. So this case here, right, this thing. Oops, okay, let me just go to the next page. It's too crowded here. So I'm going to call this property as being hidden in the shadows. So here is one example of a matrix. And in this matrix, I'm going to think of, suppose P3 and P5 were the infected people. So can you tell me which other people who are not infected are going to be actually marked as infected by our algorithm? Or just tell me who is not going to be marked as infected by our algorithm. Any of these? So P2, right? So P2, every time P2 has a test, either P5 has had a test or P3 has had a test. So P2 is going to be marked as infected. So will P1 be marked as infected?
From test 1, it will be removed.
Right. So from test 1, P3 and P5 are not involved. So P1 is not going to be marked as infected. So what we're actually doing here, the algorithm that we're mentally using to find out who is infected, who is not infected, is this. We are marking out exactly which tests include either P3 or P5. So all these tests, this is the shadow. I'm calling it the shadow of P3 and P5. And if any person is completely hidden in the shadow, then they are also going to be marked as infected. So this person is also completely hidden in the shadow. These people are not hidden in the shadow. So P1, P4, and P7 are not going to be marked as infected. This is exactly the same thing that we had said on the previous slide. It's just writing it pictorially and using the word shadows so that we seem somewhat fancy. So if I want to write this condition here, so this was how exactly P is going to be marked as infected if S is the infected set. The condition that we wanted was this. For all S, so look at this condition. Okay. So what this says is that for any S of size at most D, P should not be in the shadow of S. Okay. So let me just rewrite that there. Another way of thinking about this is, so this matrix is actually good. So right now what we analyzed was what if S is P3 and P5. But now the statement that I'm going to write is regardless of what S was. It covers all possibilities of S under the assumption that there are at most D infected people. For all S such that size of S is at most D, and if P is not in S, this implies that P is not hidden in S's shadow. So this is a completely equivalent way of talking about the algorithm 2 being a set of tests being good for algorithm 2. So let's introduce some simple notation here. If a shadow is cast by a set of C people, we'll call it a C shadow. So for example, here, this is an example. This is an example of a 2 shadow. And our algorithm 2 guarantee is exactly the same saying that nobody is hidden in a D shadow. A D shadow that doesn't include themselves. Everybody is hidden in their own shadow. But so when I say hidden in a D shadow, I'm not including the person. So this is great. We thought algorithm 2 might be nice, and it turned out to be really nice because it gave us this nice mathematical statement, which now really doesn't look at tests and people. It just looks at the matrix and asks some simple property about the matrix. It's very mathematical. Now we can actually use this concept of D shadow to argue something else. Remember our matrix guarantee? Our matrix guarantee said that if you have 2 different input configurations, infected people configurations, their output configurations should be different. And if you look at the matrix guarantee, it actually implies that nobody is hidden in a D-1 shadow. And the way to show that is if somebody is hidden in a D-1 shadow, you would show that the matrix guarantee is broken. And this statement is homework. If you find the solution afterwards, just put it on Moodle and show that you've completed your homework. This was a tutorial. I don't know why you thought you would get away without getting any homework. Call the tutorial. So now the question is, how do we make a matrix that doesn't have shadows? Just to be clear, you don't have to do the homework, but it would be useful to do it. So yeah, back to this question. How do we make a matrix which has this guarantee that nobody is hidden in a D shadow? So what we need to ensure is that everybody has at least one chance to step into the sun, to step out of the shadow. And since I'm low on time, I'll just reveal how we're going to do it. We'll make sure 2 things happen. Each person appears a lot of times. Okay, so that makes sense. If you appear a lot of times, then it's quite likely that at some point you've appeared out of somebody else's shadow. The problem with this is if each person appears a lot of times, they're also casting a very large shadow because every time they appear, that's part of their shadow. So it's a good thing. It's also a bad thing. So to make sure that that bad thing is not so bad, we'll also ask for a second condition. That if you look at any 2 people, that's any 2 columns, they should have ones in the same place only a few times. So let's just write these 2 mathematically. This one is saying that each person appears a lot of times. For every person, the number of tests where they appear is at least A times D. So D was our bound of the number of infected people. A is just some parameter, which we'll set later. The second condition, if we want to write it formally, is basically, oops, I wrote it on the wrong slide, is this one. So for any two people, the number of tests where both of them appear, so this means that the number of cases where I is in J's shadow or J is in I's shadow is at most A. What this implies is that for any person P, P is in a one shadow. So one shadow is a shadow cast by one person, then a one shadow for at most A tests. At most A of P's tests were covered. Okay, I hope this is understandable.
So Janaki has a question in the chat. So is about whether the non-shadow of each person, if you take the non-shadow of each person,
yes,
should that cover everyone?
So if the non-shadow of one person covers everyone,
I mean, if you take the union of all the non-shadows of one person.
Sorry, the union of all the non-shadows. So
yeah. So Janaki, do you want to just unmute and ask?
Yeah. So for every person, you just take the non-shadow and then take union over all persons.
All persons. Okay.
Yes.
So for example, one's non-shadow over here is test 3 and 5. And two's non-shadow is 1 and 4, and then you're taking their union.
Yeah.
I don't think that would be sufficient, because just because you're in a non-shadow of one person, you could still be in somebody else's shadow. So taking the OR of the non-shadows is not what we want to do. We want to take the OR of the shadows itself.
Okay.
Right? So, but these two conditions actually are very strong. So this is saying that a person is in a one shadow for at most A of their tests. It also says that a person is in a two shadow, that's a shadow cast by two people, for at most 2A of their tests, because one of the persons could have covered A of the tests, another person could cover another A tests, right? So P is in a two shadow for at most 2A tests. And in fact, P is in a D shadow for at most A into D tests. But P appears in more than A into D tests. So P is definitely not in any D shadow. That was a bit fast, but the idea is basically simple. If you think about P's column, it has ones in a few places. And what we're saying by property 2 is that if I take any other column, it has ones in the same place as P for very few of them. So maybe this one is covered by this shadow. And then there's another column, maybe that covers another shadow. But all of these shadows are small by property 2. So if I take at most D people and look at the shadow that they cast, that whole shadow is going to be very small. And there's at least one test left over because of the first property, that it has to be greater than 80. So I hope it's clear how these two properties ensure that everybody is outside of every D shadow. And I'm going to leave a poll here, the same poll, launch. Yeah. So the question is it clear how if I have these two properties, then everybody is outside of the D shadow? So you can think of it as how many tests of A, how many tests of person P is covered by D other people. Maybe A tests were covered by one person, another A tests might have been covered by another person, and so on. D people together can cover at most A into D tests. But it appears in more than A into D tests. So at least one of the tests that P is involved in is not covered by D people. All right, it's clear for some, it's more vaguely clear for others. So what I'm going to do is, so I'll just try to draw a quick diagram here. So actually, I see that there are lots of chats. What's that?
No, I've just been adding some summaries every once in a while. Yeah.
Suppose these are the tests of person 1. These are the tests of person 2. And property 2 says that this overlap over here, this has size at most D. Property 1 says that this has size greater than A into D. You look at person 3 and you see where they have their tests. Maybe they have to test somewhere here and somewhere here. So the overlap with this first person is in this location. Again, the size of this is less than equal to D. Sorry, less than equal to A. I'm writing the wrong term. Less than equal to A here, less than equal to A here. And so on. If you take D people, at most A into D of this is covered, but this has greater than A into D. I think I will leave it here. So the question is, what are we going to do here? We have 2 properties. Now we want to come up with a matrix that has these 2 properties. And if you think about these properties, it's saying that if you look at the locations where a person has ones, and you look at this for each player, then these locations are very different from each other. They're so different that they intersect in very few places. That's what property 2 says. So now what we want is we want a bunch of columns, all of which are very different from each other. And we know that codes have this property that any 2 codes are very different from each other. So maybe perhaps we can use this property of codes in order to come up with a matrix that also has this property of being very different from each other. After all, the code book said that it could actually be helpful when you have less tests than people. It's not talking now for some reason, but all right. I actually don't know how to do this part now, so I'm gonna leave it to Prerona. Prerona, can you show us how to use codes in order to get this kind of difference properties?
Yeah.
Sure.
Okay. So as we just saw, what we want to do is that we want to construct a matrix such that every column has a lot of ones. And if we take any 2 different columns, then the number of places in which both of them have ones is very less. This is what we saw, right? And as we just again saw, that the question is, can codes help? Okay, so suppose we are given an n prime, k prime, d prime code. Okay, then what property do such codes have? What is it that is known? What do we know? How if we take 2 different code words, they are equal in at most n prime minus d prime positions, right? That's what we know. Okay. And so now if suppose we are given an n prime, k prime, d prime code, can anyone tell me some way in which we can construct a matrix? So you see the difference, right? Here what we know is that 2 code words do not agree in n prime minus d. So it seems like, so they agree in very few places, okay? But agreement and this is slightly different. Here we are saying that they have that number of places in which both of them have ones is very few. That's what we want. Whereas in codes, what we have is that the number of places in which they are equal is very few. Okay, but it almost seems the same, right? So now suppose we are given a code, n prime, k prime, d prime code. Can someone tell me how to construct a matrix that almost has the required property? That is, let's say we want, can you tell me how to build a matrix such that given any 2 columns, the positions in which the two columns match are very few. The number of positions in which they are equal is very few. Can you tell me how to build such a matrix?
So the columns will be code.
Exactly.
Code.
Right. So the columns will be right. So you will take code words and make them into columns. Write them as columns. Okay. So suppose we are given this n prime, k prime, d prime code. Then what is the number of columns in this matrix and what is the number of rows in this matrix? Can you tell me? This is a binary code. Okay. So the alphabet is 0. K prime is the message, right? And have I written it wrong? N prime is the length of the code and K prime is the message. Yeah. Only 2 people have answered. So how many code words will there be? That will be the number of message. That will be the number of messages you want to send. Right? So how many messages can there be of length K prime?
No, it's 2 power n prime, right? Yeah, because
N prime is the length of the code and K prime is the length of the original message.
okay. So
And that's what we have been doing, right?
oh yeah. So
Yeah.
it's 2 power k prime.
Right. So the number of code words is going to be 2 power k prime. And the length of each code word is n prime. So the number of rows is going to be n prime and the number of columns is going to be 2 to the k prime. Okay. So what have we then got? We have got a matrix which almost has the property that we need. What we know is that if we pick up any two columns, that the number of rows on which they agree on is n prime minus d prime at most. Okay, and what we need, so this is what we have. And what we need is this. And additionally, we also want that in every column, there should be a lot of ones. That is also not something that codes guarantee us. Okay. Okay. Fine. So these are the two things we need. So we've created some matrix, but we want to somehow convert it into some matrix which has the required property. So this is how we are going to do it. Suppose we have this is the matrix you created just as by doing what we just did. Now what we are going to do is we are going to look at every entry. So we are going to split every row into 2 rows. Okay. And we are going to look at every entry. If that entry was 0, then we are going to write 0, 1 as the corresponding entry in the other matrix, in the new matrix. This is M, this is M prime. Okay. Whereas if there was a 1 in the original matrix, then we will write 1, 0 in the corresponding in the matrix M prime. Okay. So if we do this, then let's see what happens. So in the matrix M, the number of columns we saw was 2 to the k prime, number of rows was n prime. We didn't have any guarantee on the number of ones in any, sorry, this should be column. And any two columns agree in very few positions. That's what we knew. But what can you just fill in the blanks of what is the number of columns, number of rows, number of ones in any column, and this. What is
number of columns will just double. So number of rows.
Rows will double. Exactly. So this is 2 n prime. But what about these two? What is the number of ones? Yeah.
So earlier wherever it was matching, it would. So number of ones.
So what you said was this is going to become this. That's correct. And what is the number of ones?
Can we see why
Yeah.
that becomes that?
Oh yeah. So why? Yeah. Can you just say why you said? So this is correct. Why did you say that?
Yeah. So earlier wherever. So this is the Give me a second. This is the place where it's 1, right? So I thought this was where it was matching. Sorry.
No, but yeah. So in this, you knew that.
Oh.
So whenever two things were.
Okay. Yeah. So wherever things were matching, it was n minus n prime. So earlier at n prime minus d prime places, it was matching, and if it were a 1, it will continue to match. But if it were a 0, we made another copy of it. So like we need a copy 1 of it.
Exactly. So yeah, so maybe it will be easier to say that when will two things not match here? If two things don't match, if two columns don't have a 1 in the same position, in the same row here, it would mean that in the corresponding positions in M, there were two different elements. I think one of them was it was either 0, 1 or 1, 0. Yeah, so you can't have that. There was a 0, 0 here, but there is a 1, 1 in M prime. Okay, is this clear? I hope it's clear. But what is the number of ones? That is the easier thing to say in any column. It's n prime, right? Because whether it's a 0 or a 1, we have made at least one 1 in that entry. So if there are n prime entries in the column M, then there will be n prime ones in any column M prime, in any column in n prime. Okay. I will have to go fast, so I'll just okay. So this is the property we have. Okay. So we now have a matrix such that this is the property, and what we wanted was this to be A and this to be A times D. So what we now have is that if this is A and this is AD, then D becomes at most this thing, which turns out to be something. And this is what we want to maximize. We want to increase the bound that we assume the number of positives to be, because that's what we would want. Right? So what would that mean? So we want D to be as large as possible, which would mean that the denominator, so for a fixed n prime, we would want the denominator to be as small as possible, which would mean that D prime should be as large as possible. That is, we need chords with large distance. Okay? But we know chords with large distance. The only problem, so we know chords with good, we know chords with good distance. The only problem is that the chords are over FQ. We've seen Reed-Solomon chords, very large, nice, large distance, but they are over FQ. So the only thing we need to do is that we have to convert it to binary codes. And that is something we'll do very similar to what we just did now. And that process is called concatenation. Okay. So what was the codes currently are elements in FQ. What we are going to do is so if the entry is 1, then we are going to place a 1 in the first. So each element of FQ is now going to become a Q length bit string, and the ith element of FQ is going to be replaced by a bit string of length Q, where the ith entry is a 1 and everything else is 0. Okay. And this is how we are going to convert any chord over FQ to something over 0, 1. So that's how we are going to convert it to a binary code. And now once we have done that, the matrix dimension is going to become, is going to become Qn prime times 2 to the k prime, right? Because every entry earlier was something in FQ, and now we are going to make it a Q length bit string. So the number of rows is going to become Qn prime, everything else is going to stay the same. And so now back to the original question, if we are given a Reed-Solomon code, what we are going to do is we are going to think of the columns as the various polynomials, which is basically take the message and convert it into a polynomial. That's what Reed-Solomon codes are. And what we are going to do is we are going to evaluate those polynomials in various at various points, and then convert it to binary by doing this concatenation. Okay, that is going to be our matrix. So starting with a Reed-Solomon code, this is what our matrix is going to be, right? And the number of people is going to be the number of columns, which is going to be Q power k prime if we started off with such a code. The number of tests is going to be the number of columns, which is going to be Q times n prime. And this is what we want to minimize, because we want to minimize the number of tests. So, and we already saw that this D is, this is the property that we have for D. So it will turn out that this would imply that D prime must be at least something. And it turns out that we start off with the parameters, then it is possible to do it with only D log n square tests. So yeah, I mean, I'm completely out of time, so I don't know what, I know I went very fast, but I can't help it. And just to see the magic, so for example, if the number of people were 1,000, and suppose we assumed that there are at most 100 tests, okay? 100 positive cases, okay? So then the naive method is, in the naive method, you needed to do 1,000 tests, right? But in our method, the number of tests is going to be about D log base Dn. And
But
that,
there's a D squared, right?
No, D log n whole squared. Yeah.
Yeah, so, but D squared is already 10,000, no?
Ah, yeah, sorry.
So, okay, so typically you take the situation where N is much, much larger. It's like a
Okay,
city
okay,
or something.
Yeah. Not much.
So
larger.
1,000 is not the
That's
right
true.
thing.
Right, or not even 4.
But I mean, yeah, so something like Mumbai. I mean, yeah. Anyway, so you can imagine this being super useful.
Yes. And this comes out to be much. I didn't do the square. But when I did the calculation, I didn't do the square. Anyway, this comes out to be much smaller than the. And it turns out that this is again, I have to change everything. This is the square. And so you would ask, can we do better than this? But we can actually show a lower bound. It can be shown that you can't do better than about D square log n. So there's a log n factor difference between what we got from Reed-Solomon codes and this. Yeah, I mean, so more or less optimal. And it turns out that if you take a random matrix then of this dimension, then it actually works. But this is a deterministic construct. Yeah, I'm sorry, I went very fast.